Welcome to Tomorrow Unveiled. So this past week in space, wow. It wasn't just, rockets launching here and there. It felt like something bigger.
Definitely. More foundational.
Exactly. If you just scan the headlines, you might think, okay, another launch, another test. But our dedicated research team, they saw this clear convergence.
Right. A convergence of these foundational technologies.
Yeah, the real nuts and bolts stuff, the engineering, the validation happening right now, both in orbit and on the ground. That's actually going to build like a real space economy.
And that's the shift we're seeing, isn't it? It's moving beyond just pure exploration, which was mostly government-led for decades.
Right.
Now the focus is really sharpening on, commercial industrialization. Think rapid logistics, resilient systems that kind of run themselves, and, crucially, reusable architecture. Got to get those costs down.
Absolutely. So in our look into the source material from the research team today, we're going to synthesize these recent breakthroughs. We're focusing on three key areas. The engines powering this future, right? Propulsion. Then the actual physical stuff being built. Orbital manufacturing, habitats.
The infrastructure.
The infrastructure, yeah. And finally, the invisible network that connects it all and, importantly, keeps it secure. Communications and security.
And the stakes are, incredibly high this week. We've got Blue Origin with a really aggressive mission plan for New Glenn's second flight.
That could totally reshape the launch market.
Potentially, yes. And then there's this piece of metal literally 3D printed up on the ISS, now back on Earth being picked apart.
It feels like this is the moment space industrialization stops being theoretical and becomes, tangible, real.
Let's unpack it.
Okay, section 1, the race to reusability and next-gen propulsion. Let's start with that loud, noise-heavy lift, specifically Blue Origin.
Yeah, the preparations for New Glen's second flight are intense. Our team tracked this closely. It's penciled in for late October, maybe early November 2025.
And it's not just another test flight, is it? The research team emphasized this is a major strategic gamble.
Oh, it's incredibly audacious. They're trying to hit two massive milestones on just the second launch. First off, the main payload, NASA's Escapade probes.
Headed to Mars.
Exactly, their first ever interplanetary launch, right out of the gate. That demands a level of precision, reliability. It's a huge ask for a new rocket.
Interplanetary on Flight 2 is ambitious enough. But then there's the other objective, the recovery.
Right, and this is after the first flight earlier this year, actually made orbit, but then they lost the booster during that hypersonic reentry. It failed during recovery.
So they're trying again. I heard they nicknamed this booster Never Tell Me the Odds.
They did. It shows they know the risk. But nailing that first stage recovery is absolutely critical. It's the only way they can compete on cost with reusable systems.
So they have to land the booster and make sure the second stage works perfectly for NASA's Mars mission simultaneously.
Yeah, on Flight 2.
Yeah.
Well, your analogy earlier was good. Like trying to perfect a brand new sports car's tricky transmission while aiming to win a major endurance race on its second ever outing.
So much pressure.
And the technology involved. You've got the BE-4 engines on the first stage, 7 of them, burning methyloxamethane and liquid oxygen, which is good for reusability. Then the second stage uses a BE-3U engine. That's hydrolox, hydrogen, and oxygen. Very efficient. Gives you that high specific impulse needed for, like, a Mars injection burn.
But the tricky part is relighting those BE-4s during re-entry.
That's the critical hurdle, yeah. Relighting 3 of the 7 engines in that incredibly harsh hypersonic environment. Hot, thin air, immense stress.
Can't really test that fully on the ground, can you?
Not fully. As the source material confirms, CEO Dave Limp basically said you have to fly to test these things. Ground simulation just doesn't capture all the dynamics, the fuel sloshing, the heat, the friction.
Okay, so let's say they pull this off, both parts.
Yeah.
Why is that such a game changer for you, for me, for the whole space economy?
Because it instantly injects real competition into the heavy lift market. Right now, SpaceX's Falcon Heavy basically owns that class.
De facto monopoly.
Pretty much. And that lack of competition affects costs, it affects access, it creates potential bottlenecks for big customers. If New Glenn succeeds with both interplanetary injection and recovery, it does 2 vital things. 1, drives down launch costs through sheer competition. 2, and maybe more strategically important for NASA and the military.
The NSSL contracts, right? National Security Space Launch.
Exactly. It gives them what's called dissimilar redundancy.
Dissimilar redundancy sounds important.
It means having two proven, reliable, heavy-lift rockets from two different companies using fundamentally different engine tech. Methane versus SpaceX's hydrogen-kerosene mix.
Ah, so if one has a problem, you still have a completely different option.
Precisely. It dramatically boosts mission assurance for those really critical, expensive national security satellites or science missions. Blue Origin is taking this massive risk because they basically have to leapfrog years of development to become a major player. The market's not waiting.
Makes sense. Now, while New Glenn is attempting this giant leap, its main competitor, SpaceX, isn't standing still. They're moving Starship from testing towards, well, operations.
That's exactly the word, maturation. They're gearing up for Starship's 11th test flight around October 13th.
Now, what's the big deal about Flight 11?
It marks the first time they're reusing a super heavy booster 15, specifically that flew and was recovered previously.
Okay, so not just proving they can land it, but proving they can fly it again, quickly.
Right. It's the pivot from demonstrating the capability to demonstrating the operational reality of reuse. That rapid turnaround is fundamental to their whole plan, achieving the crazy launch cadence they need for Starlink, for Mars, for everything.
And all that launch capacity, it's creating some interesting dynamics, isn't it? Like enabling competitors.
It's fascinating. It shows how sheer capacity accelerates the whole ecosystem. Our research team highlighted this. Starship's high flight rate is enabling massive projects, even for rivals like Amazon's Project Kuiper.
Wait, SpaceX is launching Kuiper satellites.
They are. This week alone, they're prepping a launch with 24 Kuiper sats on board. It's paradoxical, right? Fierce competitors. But SpaceX's launch capacity, Falcon 9, and eventually Starship, is like this rising tide lifting all boats.
Kuiper needs rockets to deploy their constellation, and right now, SpaceX has the volume.
Exactly. Starship promises that scale nobody else can match yet.
Okay, so launch gets you there.
Yeah.
But once you're in orbit, moving around efficiently is crucial.
Which brings us to this other breakthrough, solar thermal propulsion. STP.
Yes, this is a really big validation. Portal Space Systems just achieved the first commercial demo of their STP system in a vacuum chamber.
Why is that so significant? How does it compare to what we use now?
Well, current systems have trade-offs, right?
Yeah.
Chemical rockets give you high thrust, fast movement, but they guzzle propellant. Very inefficient for long missions. Electric propulsion, like ion drives, are super fuel efficient, high specific impulse, or ISP. But the thrust is tiny. Moving a satellite takes weeks, sometimes months.
So slow.
Very slow.
Yeah.
STP aims for that sweet spot in the middle. And this flare thruster they tested. How does it work?
It's quite elegant, actually. It uses concentrated sunlight. Big, lightweight mirrors focus solar energy onto the thruster, which is 3D printed, by the way, allowing for complex shapes.
Okay.
This intense heat superheats a propellant as it flows through. But here's the key. It's a non-cryogenic propellant, like ammonia or even water vapor. Easier to store than super cold liquid oxygen or hydrogen.
So instead of burning chemicals, it just uses sunlight to heat and expand the propellant.
Exactly. Thermal energy does the work, expelling the hot gas through a nozzle.
And the performance, how does it stack up?
The research suggests STP can achieve much higher efficiency-specific impulse, ISP, than chemical rockets, maybe double, and way, way more thrust than electric propulsion.
Best of both worlds, almost.
That's the promise. Plus, using storable propellants like ammonia is a big logistical win in space. It really enables what the industry calls agile space assets.
And what does that mean practically? For missions.
It's a game changer for maneuverability. Think multi-orbit missions, rapid transfers LEO to MEO or GEO, even out to cislunar space. We're talking hours or maybe a few days, not weeks or months.
Wow.
So if you're a commercial operator needing to quickly move a satellite or maybe a defense asset needing to dodge something or get a new viewpoint fast, that speed is revolutionary. It makes satellite mobility responsive, almost on demand.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. Okay, moving on. Section 2. Building the orbital forge. Let's talk about the infrastructure needed for people and industries to actually stay in space.
Right. And a huge piece of that is manufacturing in space.
Right.
This week saw a major milestone. The first metal part 3D printed on the ISS is back on Earth.
Part of ESA's Metal3D project. It's now at EastTech, the European Space Agency's tech center in the Netherlands, right, for analysis.
Correct. They're putting it through its paces right now.
We've printed plastic tools and things up there for a while. Why is printing metal, like load-bearing metal, such a big step?
It's just way more complex. You need real structural integrity for parts that have to take stress brackets, maybe engine components someday, and managing the process. Metal printing involves intense heat.
How do they do it?
The Metal3D system used something called wire arc additive manufacturing, basically melting a stainless steel wire layer by layer at over 1200 degrees Celsius.
Okay.
And they specifically chose that method, wire arc, over using metal powders to avoid contamination. Fine metallic dust floating around in the ISS environment. That's a huge safety hazard for the crew and equipment. Wire is much cleaner.
So the tests at ESTEC aren't just looking at it, they're doing serious analysis.
Yes. A forensic deep dive. Microscopic analysis scanning electron microscopes, looking at the grain structure, the uniformity, and mechanical tests pulling it, bending it, testing its fatigue life, its ductility.
And comparing it to identical parts printed down here on Earth.
Meticulously. They need to know if printing it in microgravity changed the metal's fundamental properties.
Why would microgravity affect how the metal forms?
It comes down to physics, really. On Earth, gravity drives convection currents in molten metal. Heat differences cause movement, mixing things up as it cools, helping it solidify uniformly.
Oh, okay.
In space, no gravity means almost no convection. So the metal might solidify differently, maybe directionally, maybe with tiny voids or weaknesses, maybe the crystal grain boundaries form differently.
Which could compromise its strength.
Potentially. ESTEC needs to figure out if those effects happened, and if so, how much they matter for real-world use.
Because this isn't just about printing, like a spare screwdriver.
Yeah.
The sources kept mentioning this breaks the vicious cycle of launch mass.
What does that mean?
It's the core strategic goal.
Right.
Right now, every single screw, every bracket, every spare part has to be designed, built, tested on Earth, and then launched at enormous cost, subject to the limits of the rocket fairing.
Right. Mass is everything. If these tests show that space-printed metal parts are just as strong as Earth-printed ones, it unlocks on-demand manufacturing in space. Repairs, upgrades, building things you couldn't even fit in a rocket fairing.
That changes everything for logistics.
Radically. It shifts space operations from pack everything you'll ever need to make it when you need it, and long-term, it opens the door to a real circular economy in orbit.
Using space junk.
Potentially. Imagine recycling old satellites, spent rocket stages, melting them down and using the metal as feedstock for new parts, turning orbital debris from a hazard into a resource. That's the ultimate vision.
Wow. Okay, speaking of infrastructure in orbit, the ISS won't last forever. It's heading towards retirement around 2030. The race is on for commercial replacements, and Starlab is a big name there.
Yes, Starlab the venture, backed by Voyager, Airbus, Mitsubishi, and others, they're taking a really different design path compared to the ISS. The ISS was built module by module over many years, many launches, very complex assembly in orbit. Starlab's plan is simpler, in concept at least. One giant, 8-meter diameter, rigid metallic habitat.
Launched all at once.
That's the plan. Fully outfitted, launched on a single Starship flight. Think of it as like the instant space station approach. No assembly required.
But isn't that incredibly risky? Putting all your eggs in one very expensive basket, that one launch.
That's the trade-off, absolutely.
Yeah.
The ISS's modularity offered redundancy. If one part had issues, the rest could keep going. Starlab concentrates all that risk into the launch phase.
Oh, I do it.
The potential upside is huge savings later. Less on-orbit assembly means less complex robotics, less astronaut time spent building instead of doing science or business.
Right.
For a commercial station trying to turn a profit, minimizing those operational costs is vital.
Makes sense. And it's not just the hardware. Our research team pointed out Starlab is being really smart about building the business side early.
That's right. They're building the customer pipeline before the station flies. This recent partnership with Sabre Astronautics is key.
What will Sabre do?
They'll be like the concierge service for Starlab users, helping companies figure out if their experiment or process can work in space, integrating the payloads, smoothing the path from Earth-based research to orbit.
So ensuring there are paying customers ready on day one.
Exactly. The biggest nightmare for a commercial station is being up there, costing millions a day with empty labs. Starlab is trying to avoid that by building the user base and the support ecosystem now, selling the hotel rooms before the hotel is even built, essentially.
Smart. And none of these stations, or any long missions really, can work without robust logistics in orbit. We're finally seeing technologies like in-orbit refueling mature, right?
Yes. This is the crucial missing link, especially if you want to routinely operate beyond low Earth orbit out to GEO or the moon. Our sources confirm companies like OrbitFab are getting their refueling systems ready for
And
operations.
they're pushing a standard interface.
Yeah, the RAFTI interface, Rapid Autonomous Fluid Transfer Interface.
Hmm.
Think of it like the universal USB port, but for rocket fuel in space.
A standard bass cap.
Pretty much. A standardized physical and digital connection so any equipped tanker can refuel any equipped satellite autonomously. That standardization is everything.
Why?
It creates an open market. It means you're not locked into one provider. It enables mission extension for satellites running low on fuel, saving multi-million-dollar assets. It allows for depots in LEO, GEO, cislunar space. It basically builds the interplanetary logistics network. Without orbital gas stations, deep space missions are always limited by the fuel they launch with. With them, the possibilities really open up.
Okay, let's switch gears to the digital foundation, Section 3, the ubiquitous network connectivity and security. The big trend here seems to be integration. Satellites aren't just for remote places anymore.
Not at all. The lines are blurring fast. We're seeing this rapid convergence of LEO constellations, Starlink, OneWeb, Kuiper, with the terrestrial networks on the ground. This combined system is often called NTN, Non-Terrestrial Networks.
And it's moving beyond just niche uses.
Absolutely. NTN is becoming essential for resilience. Look at the Orange business partnership with OneWeb.
For their emergency comm system.
Yeah, the safety case. It's a rugged box you can drop anywhere to get instant Wi-Fi and comms in a crisis. But the key point our research flagged is where it's being used.
Like after that flood in Valencia, Spain.
Exactly. A major European city. The ground networks failed completely. The satellite link provided that crucial low-latency backup. So it's not just for remote oil rigs anymore. It's becoming a necessary layer of redundancy everywhere.
Even in cities. Because terrestrial infrastructure can fail.
And does. That realization is driving huge market growth. Forecasts, corroborated by our team, suggest the satellite NTN market could grow at something like 36% compound annual growth rate. Huge numbers.
Wow. Driven by 5G integration, IoT.
All of the above. Anything that needs persistent global connectivity, especially outside traditional coverage zones.
But as this network becomes so vital, it also becomes a massive target, right? Which brings us to security, especially against future threats like quantum computers. Europe made a big move here this week.
A very strategic move. ESA, the European Space Agency, officially kicked off Phase B2 development for the SAGA mission, Secure and Cryptographic Mission.
And the goal is space-based quantum key distribution, QKD.
Correct. Europe's first operational QKD system in space. It's about ensuring secure communications, especially for government and critical infrastructure, independent of potentially compromised systems elsewhere. Technological sovereignty is a big driver here.
Okay, break down QKD for us. How is it fundamentally more secure than the encryption we use now?
So today's encryption mostly relies on math problems being really hard for current computers, factoring huge numbers, things like that.
Right.
But a powerful quantum computer, theoretically, could break those problems relatively easily. QKD is different. It uses the laws of quantum physics itself. You send the cryptographic key using single photons, particles of light. And quantum mechanics dictates that if anyone tries to eavesdrop to measure or observe that photon, they inevitably disturb its quantum state.
The very act of spying changes the message.
Exactly. It leaves detectable traces. The legitimate users know immediately that the key has been compromised. So it offers, in theory, unconditionally secure key exchange. Any tampering is obvious.
And doing it from space gets around the distance limits of fiber optics on the ground.
Precisely. Fiber attenuates the signal too much over thousands of kilometers. Space gives you that global reach needed for intercontinental secure links. But
There's always a but.
there are practical challenges. QKD data rates are typically much lower than classical communications, and you need incredibly precise, clear line of sight between the satellite and the ground station.
So you need a whole network of specialized ground stations.
Highly specialized, very sensitive optical ground stations. Plus, as agencies like the US NSA have pointed out, QKD secures the key exchange, but it doesn't inherently authenticate who is sending the message, and the systems can be vulnerable to jamming or denial of service attacks.
So it's a powerful tool, but not a magic bullet.
No, but SAGA is a huge investment for Europe to build domestic capability and expertise in this critical field, preparing for that post-quantum era.
And the broader cybersecurity need across this whole space infrastructure. It's urgent now, isn't it?
Absolutely critical. Our research team consistently flags this. These space assets, communication sats, navigation, imaging, they're now vital infrastructure and their targets.
Military and industrial
For
target.
sure. For sure. We need cybersecurity by design, built in from the start, not bolted on later. We need AI constantly scanning for anomalies, for threats unique to the space environment, like radiation flips or timing attacks. And we desperately need public-private collaboration to defend these systems. They're basically the nervous system of the modern economy.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps this discussion going. Okay, let's bring it back down to earth slightly. Section 4. Challenges and the regulatory reality check. Even with all this progress, there are major hurdles.
Absolutely. We have to stay grounded in the engineering reality. Let's go back to New Glenn for a second. That second flight faces two enormous technical challenges you just can't fully replicate on the ground.
We talked about the first one, nailing that hypersonic reentry and landing the booster, which they didn't achieve on Flight 1.
Right. The chaos of high-speed, heat, friction, relighting engines. They need data they couldn't get last time. But the second hurdle is just as tough. The full power vacuum ignition of that second stage BE-3U engine.
To get the Escapade probes accurately aimed at Mars.
Exactly. Lighting cryogenic engines, especially hydrolocks, in the vacuum of space has historically been tricky. Issues with getting the fuel properly conditioned, avoiding vapor locks. It's a known failure point in rocketry history.
In this super aggressive, high-risk approach, it's purely driven by the market, by the need to compete.
Entirely. They can't afford a slow, cautious, step-by-step development like in the old days. To challenge the established players for those big government and commercial contracts, they have to take these calculated big swings. They need to catch up fast.
Another challenge, maybe less glamorous but just as critical, is regulation. The rules are struggling to keep up with the tech, aren't they?
That's putting it mildly. The pace of innovation, especially in launch, is just overwhelming the regulatory frameworks we have.
Because those rules were written for a different era. Few launches, government-run, mostly expendable rockets.
Exactly. Now you have companies talking about potentially over 100 launches per year from Florida alone. The existing systems for launch licensing, spectrum allocation, reentry safety approvals, they just weren't built for that volume or complexity, especially with reusable vehicles landing routinely.
And it creates bottlenecks.
Huge bottlenecks. Our sources highlight the complex situation, particularly in the U.S., where you have split responsibilities. The FAA handles launch and reentry safety. The FCC handles spectrum, communications, and increasingly orbital debris rules for mega constellations.
So companies have to navigate multiple agencies, multiple reviews.
Which slows everything down. It risks stifling innovation, maybe even pushing companies to look at launching from countries with, shall we say, more streamlined processes.
Do the regulators see this problem?
Oh, absolutely. The US FCC declaring October 2025 Space Month to specifically focus on modernizing these rules is a clear sign. They're talking about creating a licensing assembly line approach, especially for proven reusable vehicles.
Trying to stop bureaucracy from choking the golden goose.
Essentially, yes. They recognize that clear, efficient regulation is now vital infrastructure itself for the space economy to thrive.
And finally, overarching all of this, geopolitics. Every advance we've discussed has dual-use potential, doesn't it?
It's unavoidable. Orbital servicing tech that can refuel a friendly satellite could also, in theory, interfere with an adversary's. Heavy-lift rockets launch commercial satellites, but also military ones. Mega constellations provide internet, but also persistent surveillance potential.
Raises big questions about transparency, norms of behavior.
Huge questions. How do you verify intentions in orbit? What are the rules of the road? These are becoming urgent diplomatic challenges.
And our research team confirmed activity isn't just happening in the West. This is global.
Definitely. We saw corroborated reports from China's commercial sector. Things like their liquid-fueled Kinetica 2 rocket getting ready for debut, expanding sea launch capabilities for flexibility, hints of successful propellant transfer tests way out in GEO with their Shijian satellites.
So rapid development happening everywhere.
Across multiple continents, driven by both commerce and strategy. Which just underlines how crucial it is to get those international norms and diplomatic channels working to avoid miscalculation or conflict in this increasingly crowded, contested space domain.
Okay, let's try to wrap this up. Key takeaways from the week.
I think 3 big trends really stand out, validated by this week's events. First, launch duality. The heavy lift market is genuinely shifting from monopoly towards real competition thanks to these high-stakes reusability efforts like New Glen's big test.
Right.
Second, in-space industrialization is becoming real, that metal 3D print getting tested, the maturing refueling tech. They're building the actual physical supply chain needed to stay and work in space long-term.
Mm-hmm.
And third, ubiquitous connectivity. Satellite networks, NTNs, are no longer just backups. They're becoming a fundamental, integrated, resilient layer of global comms, which in turn demands new security approaches like QKD.
And looking out, say, 5 or 10 years, where is this heading?
You're looking at a future where orbital maintenance, repairs, component swaps happen routinely, on demand, in orbit, where the difference between connecting via satellite or a cell tower becomes seamless to you as a user, and where multiple commercial space stations are operating in Dilio simultaneously.
All enabled by cheaper, more routine access to space.
The foundations are being laid right now. It's not science fiction anymore.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the future of orbital manufacturing and the high-stakes New Glenn mission. But I want to leave you with this final thought. Building on that metal part being analyzed at East Tech right now.
Yep.
If the first metal part printed in space is now being tested back on Earth, what's the first truly essential component that gets manufactured only in orbit? Something so uniquely suited to microgravity production or so vital that making it up there frees us completely from having to launch it from Earth. What's that first product that defines the success of space industrialization?
What unique thing can only be made well in space? That's the billion-dollar question, isn't it? Lots to think about there.
Thank you for joining us for Tomorrow Unveiled. We'll see you next week.